Hey everybody, I would like to talk about game theory today. It's a topic I'm very interested in for a lot of reasons. It's a field of math as well. I play a lot of poker, so it's quite relevant to me personally, but also to the world, especially if you're following any of these wars going on. So, most people, when they talk about game theory, they're going to discuss this thing called the prisoner's dilemma, which I think a lot of you have heard of. I might do a separate video about that because there are interesting things to say about the prisoner's dilemma. But I'm going to talk about something completely different today, and that thing is toll roads, which are sort of considered the boogeyman if you drive a car, which I actually don't, but I've heard they suck. And I'm going to make an argument using game theory that toll roads actually might be useful and good for the people. So bear with me. I'm going to set up a small model environment to discuss this topic. Let's imagine there's 100 people and they need to get from point A to point B. So let's say over here is point A. Say this is the residential area where everyone lives, and this is point B. Maybe point B is a business district. Maybe everyone has to go to work in the morning, and that's why. And we've got 100 commuters. Let's just write 100 people, because I don't want to misspell the word commuters. People. Alright, cool. And they have two options for how they want to get from point A to point B. The first option is they can take the trolley, or the tram, or whatever, or a train. These are my train tracks. Now, the train is quite nice, and it fits everyone. All 100 people in the town could fit on the train. So if you take the train, it's going to take you 20 minutes. And it doesn't actually matter how many other people are on the train. It'll always take you 20 minutes. The other option is a good old-fashioned road. Now, roads have problems with congestion, obviously. So on a road, how efficient the road is going to be partially based on how many other people are on the road, right? If no one's on the road, it's a freeway, it's going to go a lot faster. So we're going to think of some kind of function to describe how long this road's going to take, and it's going to be based on how many other people take it. Let's say that this road is going to take 5 minus x over 4 minutes, where x is the number of people on the road. So if you're the only person on the road, 5 plus x over 4, that makes no sense, yeah. So as x gets bigger, the road gets less efficient. So if you're the only person on the road, it's going to take you 5 minutes and 15 seconds, because there's only one person on the road. And as this x grows, the road becomes less and less efficient. Alright, now this is still too simple, because people have different preferences. So, and I'm going to talk about the toll road here. So we're going to talk about everyone's preferences in terms of money or value. We're going to express everyone's desires in a monetary way. We're going to think about it like money. So let's talk about how badly these people want to make it, or how much people care about reducing their commute time. So let's say that we have 40 people that are really impatient. Now for them, they really care to minimize their amount of time on the road. Let's say that they value getting there is 100 minus 2t, where t is the amount of time it takes them on the road. So if it takes them 20 minutes, they take the tram, it's going to be 100 minus 2 times 20, so they're going to get about 60, yeah. And they obviously want to minimize this number. So their goal is going to be to minimize this. This is what we call like a value function. I should actually just write like v equals. It doesn't actually really matter. Now, for the other 60 people, let's say that they're a little bit less impatient. They care a little bit less about getting there on time. They still don't like time. They'd like to minimize it, but they're not as interested in that as our impatient people. So their value function is going to be v equals 100 minus t. So time is still bad, but they don't care as much about it. Now what I'm going to argue to you in this video is that if I placed a tolling booth here and added a fee, there exists some prices I could charge that would be good for everybody in this system, even the people who have to pay the fee. Before we do that, let's talk about what's going to happen naturally with no toll booth. Now we're going to make a lot of assumptions in game theory. Mainly is going to be this thing about everyone being a rational agent. So we're going to assume for the sake of argument that, you know, there's no crime on this train. It doesn't really matter. The idea is that like they're going to be completely indifferent. All people are trying to maximize here, or minimize I should say, is the time. Everyone just wants to get the most possible value they can out of their trip, and their value is just based on time. So what's going to happen in this system? Well, if the system was to stabilize, if you were taking the tram and switching to the road was more beneficial to you, then you would switch to the road. And if you were taking the road, but it was taking you more than 20 minutes, right? You'd want to switch to the tram. So everybody would have to keep switching, going back and forth, until eventually everyone's in a situation, this is what we call a stable situation in game theory, where no one can benefit from changing their decision. In poker, we call this being unexploitable. The idea is that basically the road has to also take 20 minutes for this to be a stable system. So if the road was to take 20 minutes, we can say 5 plus x on 4 would be equal to 20. And if that was the case, we would have x on 4 equals 25. Which means that x equals 100. Hold on 1 second, sorry. Oh no, sorry, I've messed up. Yes, okay. That shouldn't get 100. Sorry, subtracting 5 from both sides. Yes, that makes sense. X should be 60. So in an ideal system, we would have exactly 60 people on the road and 40 people on the trolley with no toll. And in this situation, everything would be well balanced, meaning that no one has an incentive to switch. If you're doing either mode of transport, switching is bad for you. So everyone's going to stay. And in game theory, this is called a Nash equilibrium. And you're going to have to watch a trolley problem video a Prisoner's Dilemma video to learn more about a Nash equilibrium. But that's the idea. So in this system with no toll, let's calculate the payoffs for both of our classes of people. We're going to start with the impatient people value. So I'm going to V of I means impatient. Well, no matter what happens, they're going to take a 20-minute commute. So an impatient person is going to be doing 100 minus 2 times 20. The impatient person has 60 as their value. And our patient person, which I'm going to call VP, the value for the patient person is just going to be 100 minus 20. So they're getting 60. So even though the patient people are getting more value out of the system, they still have no incentive to switch, because at the end of the day, both people are still just trying to minimize the amount of time. Alright, now let's consider adding a toll to our road. I'm going to keep these no toll things here. In fact, I might screenshot them and move them to another part of my screen. Let me just... So we've got our no toll calculations. Let me just move those. Copy, paste. Oh, here they are. I'm going to keep them up here. Now let's imagine adding a toll. So I've got a toll booth, and let's say, well, the people who are impatient are going to get quite upset about anything that happens here, really, just because they are impatient. But let's say I'm going to try and create a system where I want all the impatient people to prefer this road and pay a small toll, and all the patient people to prefer this road, which means that I want to get exactly 40 people to prefer this road here. So let's just imagine if 40 people were to prefer this road here. Let's think about how long it would take to drive on the road. So we have a function for that, so it's going to be 5 plus 40 over 4, which is going to be 10, which is going to be 15. So in the system that I'm going to try and create, this road is going to take 15 minutes. Now, obviously we don't have a natural equilibrium anymore, because if one road takes 15 and the other road takes 20, in a vacuum, everyone's just going to want to rush to the 15 road, and then it will no longer be a 15 road, right? That's the issue here. That's why I want to put a toll booth here. My goal here is going to be to price out all the people who don't really care that much about time, only a little bit, but price in all of these people who really care about the time. So let's add some cost C, a price C for my toll. The toll is going to be C dollars. And we're now going to explore what values of C create a better system. So for my impatient people, V of I, their value is now going to be 100 minus 2 times, well now it's going to be 15, minus C. Remember, C is going to be whatever cost I'm picking here, right? So this is going to simplify to 70 minus C. And in order for the impatient people to value this system over the other system, this value has to be higher than their value in the other system. So in the other system, they were getting 60 worth of value, and here they're getting 70 minus C worth of value. So all I need is that 70 minus C is less than 60. Do a bit of maths. Let's add C to both sides and subtract 60 from both sides. We end up with this needs to be more value than this, sorry. Let's add C to both sides and subtract 60 from both sides, and we end up with C has to be less than 10. So if the cost was greater than 10, even the impatient people wouldn't want to pay this toll, given that they spend 15 minutes instead of 20 minutes. So the cost has to be less than 10. So let's save this fact here. So in order for the impatient people to prefer this system with the toll over the default system, the cost needs to be lower than 10. All right, now let's talk about our patient people. We need to make sure that the patient people don't just want to switch. Because if the toll was $0, right, and this is 15 and this is 20 minutes, they're going to think, screw this, I'm going to get off this tram and take a shorter drive. So the cost has to be something. So we're going to do a very similar thing for VP. So let's say VP is going to be the value for this person, the tram. It's going to be they need to prefer this trolley over this other thing with the cost. So when this person is not using the trolley, their value is going to be 100 minus T, which is 20. Their value is going to be 80, which you've already calculated. And if there's a cost involved to switching, it's going to be 100 minus only 15 this time, but also minus that cost, which is going to be 75 minus C. So in order to make sure that these more patient people don't want to switch, all we need to do is ensure that 75 minus C is is lower than 80. let's subtract from both sides. Negative c is less than 5, which means that c, let's add c and subtract 5, so that means that c has to be greater than 5. Cool. So our cost has to be it has to be greater than 5. And if it's not greater than 5, our trolley people are going to be like, nah, screw this. I'm just going to go on the road where it's better. So it looks like we found a good range for our cost. So our cost needs to be somewhere in between 5 and 10. And if that is the case, both classes of people, the impatient and the patient, will be happier. So yeah, that completes the end of the problem. I guess I didn't really phrase it as a problem, but I think this idea is really, really interesting. So game theory has just told us that we have this situation that isn't too far-fetched, where the system is completely natural, and all we've done is added a toll road, which is, infamously upsetting for humanity, but it has made everyone's lives better. There's less people on the trolley, so these people are fine, they're happy, and these people are paying a price that they were willing to pay. All we needed was a price for the toll that prices out these people who don't really care that much, but makes it worth it to these people. So yeah, I'm not saying that all toll roads are useful. Obviously, I'm not saying that, it's crazy. But I'm just giving a very simplified example of where a toll road might be helpful. So yeah, sometimes, and this can be true in all sorts of places on the road. You probably heard of this like meme about adding one more lane to the road and how that can actually have negative effects. That's the same thing here. When you introduce something into a game theoretic system with a lot of actors that try to act rationally, it can create a lot of problems that you won't have foreseen. There's a very similar argument to be made with, there's a road that goes around a hill, and you can pay a lot of money to cut down the hill or whatever, or build a tunnel, and then the road goes through the hill. And even if the road has less distance, it doesn't help anything, because the reason that road was taking so long wasn't the distance, but it was some bottleneck at the end of the road, right? So there are all these things with roads and civil engineering where our intuitions about what will work might actually make a system worse. And this is the opposite, where something that seems just objectively bad, a toll road, has made everyone's lives better. But yeah, that's all I have to say about toll roads. So thanks for watching, guys. Cheers.